Okay, thanks, Marcelo. So thanks for having me here. Like Marcelo said, my name's Tony Lee. I'm a grad student at Stanford, and I'll be talking today about connecting CO intensity mapping to galaxies, essentially galaxies and galaxy formation, but more specifically to molecular gas and star formation in high redshift galaxies, where high redshift here is above redshift 2. Okay. So let me start with a little bit of motivation by way of a somewhat simplistic example. Here, what I'm showing is a cross-section of the co-moving volume of the universe. And where we are is on the left here, and we're looking out to the right. And so these dotted circles show surfaces of constant redshift. Right? And so this is an exciting time in cosmology because galaxy surveys are pushing to higher and higher and higher redshifts. And so we're reaching well into the epoch of reionization with Hubble deep field images. But suppose for a second that you have a particular galaxy survey that's about 2 degrees squared, and you're complete down to a certain luminosity, let's say Milky Way luminosity, out to a redshift of about 2. So this is roughly about the size of the Cosmos galaxy survey field. And now suppose you want to keep the same observing time, but you go a little bit narrower in area. And so you can just use these simplistic relations. You say the observed flux is inversely proportional to the luminosity distance. And your minimum flux, so your flux sensitivity, is inversely proportional to the square root of your on-source time or proportional to the square root of the area. Right? And so if you go a little bit narrow in your area but keep all the same parameters, let's say 6 arc minutes squared, you can get out to a redshift of about 9. This is about the size of the Hubble ultra deep field. But if you want to go a bit wider in area, right? So let's say a few hundred square degrees, then you can only get out to a redshift of about 0.7 or so. Okay. So just to make this a bit more concrete, what I'm showing here is a plot of various far infrared surveys. And this is just showing their exposure versus their area. Excuse me. So this is just showing their exposure versus their area. And each of these dots is a different survey. Right? And the basic idea here is still exactly the same. Down and to the left is narrow and deep. Up and to the right is wide and shallow. And you have this intrinsic trade-off between the two extremes. Right? What this means is that at redshifts above 2, it's hard to observe typical galaxies in complete samples over very wide areas. And this trade-off here is rather fundamental, right? Because as long as we're collecting photons, we're going to run into this problem. There's no way that we have at the moment to go both wide and deep, right? But this issue presents a challenge for 2 fields in particular, 2 related fields in particular. The first is cosmology, and the second is galaxy formation. So for cosmology, if you're trying to trace large-scale structure, for example, if you're trying to trace BAO, right, or the linear power spectrum in general, you need sufficient number densities of galaxies over sufficiently wide areas as well. And for galaxy formation, any individual galaxy you might observe, for example, at redshift 9 or 10 or 11, needs broader context. Because at some point, you need to put them in the context of their broader populations, which are evolving and interacting. Okay. So essentially, our ability to probe cosmology depends on our understanding of what's probing it to some extent. And then our ability to understand galaxy formation depends on our understanding of the framework that they actually form in. Right? And so intensity mapping targets this observational gap where we can't go both deep and wide at the same time. OK, so I should say a bit about what intensity mapping is. I imagine it needs a little bit less introduction here, since there's work on CHIME going on here. But what intensity mapping is, in a sentence, is you focus on a single spectral line, and you map it out across cosmological volumes. And so to do this, you have an additional trade-off to make. What you do is you fuzz out your resolution a little bit. So you have moderate angular resolution. And so you're aggregating flux from multiple galaxies on larger scales, where larger here is on the order of co-moving megaparsecs or more. But you have higher frequency resolution. So essentially, you get to do tomography along the line of sight. Right? And since you're focusing on a single spectral line, the frequency you observe it at gets you an automatic redshift for free. Right? So you need this high frequency resolution to resolve line of sight structure and fluctuations. So there are several potential target lines. So 21 centimeter, I imagine many people are familiar with here, since CHIME is probing that out to a redshift of about 2 to 3 or so. There's also SKA, which is planned to probe potentially hydrogen well into the epoch of reionization. But there's also C2, which is being worked on at Caltech with the TIME collaboration, and Lyman Alpha, which is being proposed with the SphereX collaboration. For this particular talk, I'm going to be focusing on the CO10 line. Right. So let me say a bit more about the CO10 line. So CO is here carbon monoxide. And so carbon monoxide has a twofold advantage. One is it has scientific significance, but two, it has a practical advantage. So the scientific significance is that it traces molecular gas, or H2, at low redshifts. So it's commonly used to trace molecular gas, the idea being that if it's cold enough to form H2, it's cold enough to form CO, and CO is the most abundant molecule after H2. We can't observe H2 directly as easily, just because it doesn't have a permanent dipole moment. CO does have a permanent dipole moment, so you get these rotational quantum modes, rotational quantum transitions that gets you this ladder of emission frequencies. Okay? But because it traces molecular gas, it's also strongly correlated with star formation. Right? And so if you're tracing molecular gas, to some extent you are tracing star formation. At the very least, you're tracing the fuel for star formation. But this ladder that I mentioned, this ladder of rotational lines, is what brings up the practical advantage. And the practical advantage is you get multiple lines essentially for free, especially in these lower few lines. And I won't get to say too much about it in this talk, but for example, the 1.0 line is at 115 gigahertz. The 2.1 line is at 230 gigahertz. 3.2 and 4.3 and so on and so forth. They're just integer multiples of 115 gigahertz. What this means is that you can pick two different frequency bands at the right ratio to each other, and then cross-correlate the signal in the two bands to get the CO-only signal. Because especially these lower transitions have such low excitation temperatures, you can reasonably expect that if you see something emitting in CO10, you can probably also see it emitting in 2.1 for free, essentially. Okay. So let me show you what this ladder looks like in a typical galaxy spectra. Actually, this is a bit brighter than a typical galaxy spectra. But this is a mock-up of a very luminous galaxy, redshifted to about Z of 5 or so. So the line that we're focusing on is this line here, the CO10 line. Right? And it lies on the redward side of this very large thermal dust continuum. The other CO lines are shown as this ladder of spikes here that goes upward and upward and upward. And on the redward side of the CO line is continuum emission from synchrotron and free-free. So it lies in this microwave radio range. And if we're observing it, we'll observe it around, I'll mention it later, but around redshift 30, or sorry, frequency of 30 gigahertz or so. So there is a real instrument motivating this, like Marcel mentioned, and that's the CO Mapping Array Pathfinder. So the abbreviation we're using for that is COMAP. And throughout this talk, it'll be indicated with red, and the full experiment will be indicated with blue, but I'll mention that again. The Pathfinder is currently under construction through a collaboration of Caltech, JPL, Stanford, Maryland, and Miami. But it's a single-dish experiment in the microwave regime, which we're modeling in this talk as having 6 arc-minute resolution, so a 6-meter dish, scanning over a 2.5 square degree area. And the frequency band that we're using is 30 to 34 gigahertz. So in a nutshell, what that does is that images CO10 from redshifts of 2.4 to 2.8. The full experiment we're modeling as essentially a more sensitive experiment. It'll have lower noise. It'll cover a wider area. And it'll have better resolution at about 4 arc minutes or so. But again, it covers the same band at 30 to 34 gigahertz. OK. So the focus that I mentioned was 2.4 to 2.8. And roughly speaking, that's between redshifts 2 and 3. And let me motivate that a little bit by saying that redshifts above 2 are generally referred to as the epoch of galaxy assembly. And so this is a period of rising or peak cosmic star formation. The issue is we don't really have a great understanding of molecular gas and its relation to star formation in this era. And what I'm showing here are essentially star formation histories and molecular gas histories. So to the left is a present day. To the right is further back in time. On the left, I'm showing the cosmic star formation rate as a function of redshift. And you can see that as you go further and further back, you get this period of rising star formation. And the peak is really around here. And it's within this region that we're probing. Right? And so we have data going all the way back to redshift 8 or so. It gets a bit sparser, but we still have information on star formation rates back to those redshifts. On the right, we see something pretty similar, and it looks also pretty impressive until you realize that almost everything on this plot is modeled. That there's not really much data here. Right? You get these lower limits from various observational probes, but we don't really know too much about the cosmic molecular gas content. Right? And we need to if we want to understand what's fueling star formation and how galaxy formation is proceeding as you get to higher redshifts. So essentially, if we can manage to probe CO, we can probe molecular gas. If we can manage to probe molecular gas, we can probe the fuel for star formation and galaxy formation. OK. So then the basic questions that are focusing this work right here are twofold. The first is, given what we already know, what can we expect to see? So in essence, given current data that we have, what is the predicted brightness and the power spectrum of the CO intensity mapping signal? And the second question is, what can we actually expect to learn? Right? So nature doesn't care what we think of it. So if we actually do see a signal, how well can we actually constrain the molecular gas content of galaxies, of the actual emitting galaxies as a population? OK. So I'll focus on the first question, which is, what can we expect to see? And in order to make predictions, we need to have a model. And this model is influenced and informed by previous models of CO intensity mapping that have come before. But in broad strokes, essentially, we start with dark matter halos, and then we populate them with galaxies which have assigned star formation rates. We convert those star formation rates to infrared luminosities. From those infrared luminosities, using relations in the literature, we convert them to CO luminosities. And then we add on some scatter, which is also constrained. So at the end of all of that, we start with dark matter halos, and we get out 3D CO intensity maps and their power spectra. So the net effect of this model is something like this. What I'm plotting here is CO luminosity versus halo mass. So this is essentially the galaxy halo connection, but for CO luminosity. So what goes in is on the x-axis. What comes out is on the y-axis. And this black line here is the mean relation that we use. The colored lines show previous relations in the literature. And you can see we're broadly consistent with previous models that have come before. One thing you might note is that our model is not linear, which almost seems like a very trivial thing to say, but it actually does affect the shape of the power spectrum that we get. And this will become important later on. Every single step in this model is empirically constrained by whatever limited high redshift data we have. It may be somewhat sparse, but we work with the data that we do have. OK. So for a bit more visual intuition on this, what I'm showing here is a 3D rendering of the halos in one of our renditions of the Pathfinder volume. And I'm plotting also for reference here the redshifts that these halos are at and the observed CO frequencies. And the observed CO frequencies that the halos are at. Okay? And as you go to the right, you're going further back in time or to higher redshifts. So if I plot out projections or slices in either direction, on the left, I'm showing the sky projection in the lowest redshift slice of all the halos. And then on the right, I'm showing, basically rotating that by 90 degrees, I'm showing what the halos look like along the line of sight in a slice which is equivalent to the beam width of our experiment. And what you get out of that is a 3D CO intensity map, and these are the slices converted to CO intensities. Right? So you're no longer resolving individual galaxies, but you still get the same large-scale structure. And you can just visually see that they're tracing out the fluctuations are tracing out the same clustering signal. Okay. And the strength of the signal is about, on average, about a Kelvin or so, a microkelvin or so, excuse me. Right? And so we're looking at a very faint signal, to be sure. And this is why you need frequency resolution along the line of sight. Without that frequency resolution and these slices, this all just gets smeared out. Right? So you need this ability to do tomography. OK. But the actual main observable, so to speak, that we use, or what we convert that to, is a power spectrum. And so we take that 3D intensity map. We do a 3D Fourier transform on it. And we spherically average that 3D Fourier transform after squaring it into a power spectrum. And this power spectrum here, this is a spherically averaged power spectrum, encodes cosmological structure. So it encodes the clustering signal, essentially. And the fiducial prediction is shown by these. The fiducial prediction we have is shown by these red and these blue lines. So the Pathfinder, again, is the red line. The full experiment is the blue line. And these dotted lines show the limits, the error bars that we would get from noise and resolution combined.
What kind of TSIS and number of pixels does it have?
Yeah, so TSIS is, for the Pathfinder, 35 Kelvin. And then number of pixels is 19 dual polarization pixels. 19. And so for the full experiment, we're a bit more ambitious. So this is a longer-term model. So TSIS, I believe, is about 30 Kelvin. I should double-check that, but about 30. And then the number of feeds is 500 dual polarization. Right, so it's a lot more ambitious. And the idea is it would also potentially be an array of dishes as well. Okay. So what we see here, or at least when you plot the power spectrum over the error bars, the fiducial prediction appears to be detectable. Right? So what I'm showing on the bottom here is a detection significance of each mode versus the wave number. But if you integrate this over the entire range of k that we're probing, the entire range of scales that we're probing, and you make the strong assumption of uncorrelated errors, then you get that the Pathfinder has a total detection significance of about 7.8 sigma, the full experiment of about 140 sigma. It depends on your binning, of course. It depends slightly on your binning. But these numbers essentially stay in the same neighborhood.
How many hours is that?
Yeah, so this is the Pathfinder is 2 years, but with 35% observing efficiency. So 2 years converted to hours times about 35%. And the full experiment is 3 years.
How much sky?
So Pathfinder is 2.5 square degrees, and the full experiment is 6.25 square degrees. Okay. So this power spectrum, like I mentioned, encodes cosmological structure. But because we have a model that converts halos to galaxies, it also encodes the population, the properties of the galaxy population. Right? So briefly speaking, if you change the normalization of the relation, if you basically just scale everything up or down, your power spectrum also gets scaled up and down. That's probably not terribly surprising. If you start to introduce halo-to-halo scatter, or in other words, if you introduce more jitter about the mean relation, you start to get this high K signal looking more and more like shot noise. So essentially, this hump down at low K, or large scales, has been referred to as a clustering signal. And then this straight part up here at high K, or small scales, is the shot noise signal. So as you introduce more and more scatter, basically the halo-to-halo scatter washes out any sort of structuring or clustering signal that you might see. Right? And so you have to worry about sample variance, within your volume alone. But this one case over here, where it seems like it's almost all shot noise and has a very large scatter, that's a scatter of about 1 dex, which we think is unrealistic.
Have you tried to model this with the halo model?
What do you mean by halo model?
Well,
with the analytic power spectrum. Yeah, so you can do that. You can do that, but this is a particularly nice framework, even though it's more expensive, because it gives you essentially a framework for studying galaxy formation and other interacting processes. We don't model that here, but it's good to have that going forward. Okay. And also, depending on how you weight faint galaxies, this clustering signal, again, this hump at low K modes, can also change. Right? So what this is actually doing is it's varying the relation between infrared and CO luminosity. And these are various fits that have shown up in the literature. But what you're seeing is that as you weight faint galaxies more, which corresponds to moving the power spectrum this way, your clustering signal increases. Okay. So this all suggests that we actually can use CO intensity mapping to constrain the underlying galaxy population. And so now I'm going to focus on the second question, which is what can we expect to learn? Right? So from a mock observation that we generate, how well can we actually constrain the CO, which is roughly the molecular gas content of the underlying population? Right? So essentially, we're doing forecasts of constraints here. And so in brief, what we do is we generate a mock power spectrum and error bars that would essentially simulate the observation that we would see from both the Pathfinder and the full experiments. And we feed them through an MCMC procedure, which is attached to our CO model. And then we get posteriors for the various parameters in our model. Okay, so what goes in is a Mach signal, which is generated for both the pathfinder and the full experiment. And there are also priors on the parameters where available. We get the priors from constraints from existing observations, or they're deliberately broad. Right? So we don't want to overly constrain our problem at the moment. And then what comes out is posterior constraints on the galaxy population. So in particular, we have constraints on two statistics for the galaxy population. And the first I'll mention is the infrared-CO relation. So this is a relation between galaxies' infrared luminosity and CO luminosity. With assumptions, this is a rough proxy for the star formation rate versus the molecular gas content. So star formation rate versus the fuel for star formation. Right? And so the slope of this line tells you something about how the gas consumption time for galaxies will vary across different galaxy types. So at the bright end here, you have a lot of quasars and ULIRGs. At the bottom here, you have more normal galaxies and spirals. Most of these points at the low luminosities are from low redshift. Right? So we don't really have a lot of data on high redshift fainter galaxies. Okay, but this has been plotted and fit to a number of data in a number of papers in the literature. So I'm just showing 3 here on the right, Dadi et al., Grave, and this one here. But what we get from our MCMC procedure are constraints on this relation. Right? So the constraints from the Pathfinder experiment are shown in red here. And what I'm showing are the 1 sigma credible intervals on this relation. Our fiducial model is this black line here. So that generated the signal that went into this. Again, black line here. And the various literature fits that I showed before are these dotted gray lines. Okay.
That's marginalizing over your mass function,
over all the other parameters, essentially.
Because you assume that you know exactly the mass CO against mass halo a priori already, and then you marginalize only within that scenario?
So we...
I would have thought if you allow that to float, anything goes.
Right. So let me see if I understand your question. So you're saying, so just to be clear, we don't actually calculate molecular gas first. We don't calculate H2 content. So this is an empirically constrained model. So we start with star formation rates, which have been constrained using basically simulations and existing literature data. Right. And so there are constraints on that. And then we go to infrared luminosity, which has a normalization associated with it. We have a broad prior there. And then from infrared luminosity, we go to CO luminosities, right?
Yeah,
and so
luminosity is a function of mass, right? I can even look at the function that you have.
Yeah.
Of how much CO luminosity a galaxy, and at the end of the day, in your model, I think all that goes into your model is you need to know the mean and scatter of CO luminosity as a function of halo mass.
Sure. Yeah.
Now that's a free function of 2 variables. I've got two functions, both function of mass, scatter, and luminosity.
Mm-hmm.
And is this marginalizing over all possible forms of that function, or do you say you know that function and that's, what?
Yeah, so we assume a functional form, right? And the functional form is parametrized. So in this case, you have an alpha and a beta that parameterizes the IR-CO relation. We have basically parameters which dictate how you convert from one quantity to the next, to the next, to the next. And we put priors on those parameters.
So no,
right?
it's not completely allowed.
Right, so there is a relation that's been assumed. Right. But so the question is, how do you have a relation that's sensibly extrapolated in a parameterized way to lower mass galaxies, right? And so we think this is a pretty reasonable way to do it because we're just essentially modeling the tail end of that function as a power law. So basically the faint end of that function as a power law, and then we're just allowing the slope and the normalization of that power law to vary. Right?
I mean, just an example. Obviously, it's good to see something and measure something.
Yeah.
But it is known that the CO luminosity depends on atomic properties. So it's not to know gas or gas. They could be, they could be in the wrong state. They may not be excited. They may not say.
Yeah, it might.
There could be huge gas.
Right.
Unknown at that redshift.
Right.
So in the end of the day, you measure a power spectrum.
Mm-hmm.
At 7 sigma, you're measuring one number at 20% accuracy and 2 numbers at maybe 50% accuracy each, right? That's the limit of what you'll ever be able to get out of the 7 sigma.
Sure. Right.
So in practice, you're probably measuring some combination of parameters. Basically, one combination. 7 sigma is measuring one combination of parameters.
Right.
At the factor that's kind of 7 sigma basically.
Right.
and I suppose you could make it that you could project it onto a COIR relationship, assuming that there's some other model underneath, or you could say that this is a global constraint because you don't really know that model.
Yeah, so it's a question of how you want. You can swap out different components of the model if you like, right? So you can make this modular and swap.
You could use exactly the same argument. Why did we bother with the CID? Because there are too many control parameters that you get to dial around. So you don't have a choice.
Well, you're doing because it's coming your way anyway, so you have no choice. But the CID you're measuring is just coming at you. And you can deal with it. Well, but this is they're spending money to try to find something which normally is just coming complete.
The CID, okay, the CID was actually targeted. You're saying that sadly it's contaminating the primary anisotropy. To be sure, but anyway, notoriously, it's been a great set of observations to make. Everything's been highly refined, but it's still true that there are many parameters. And the only way forward is the crosstalk between observation and theory, because the theory by itself isn't powerful enough to deal with it. This is even more true with carbon monoxide. So then the question is, what is the path forward? And the path forward will be a combination of focused observations, as many redshifts as you can get, as well as this kind of approach.
Right.
So at least that's what I do. So anyway, I'm trying to be a little more optimistic than you are lately. We shouldn't dismiss the subject before it begins.
So the broader point I wanted to make towards the end is this is not going to stand in isolation, right? So it's exactly what you're saying. This is one component of many different observational probes of the high redshift universe, right? And so that's sort of how I'm viewing this right now. Right. So. Right, these are constraints on the IR-CO relation. Within about 1 sigma, or the 1 sigma posterior constraints, you see they're basically consistent with the other relations in the literature. The main point here is that you're getting this information from imaging the faint galaxies directly. In aggregate, to be sure, but you're getting the emission directly from the faint galaxies, right? Rather than taking a relation that's been fit to some galaxies up here and then just extrapolating downward. Right. So the second constraint that we get is on the CO luminosity function. And so this is essentially, this is a population distribution. Up and to the left is fainter and more abundant. Right? And so the fiducial CO luminosity function that we get from our model just looks like this within our volume. Right? So this is the true luminosity function, so to speak. If we put in an intensity map that's seen by our Pathfinder experiment, we get these constraints on the CO luminosity function. Right? So these are actually now the 2 sigma posterior constraints, the posterior credible intervals. Right?
And here you are letting it have any shape.
Here we're letting it have, it's essentially the output of all of our model, right? So it depends also on the halos that are within our box. Right? And if we put in the full experiment, the blue shaded bands show you the posterior constraints, the 2 sigma posterior constraints on the luminosity function, right? So again, the fiducial model, or the output of the fiducial model, is consistent with both of these within 2 sigma. And actually over a pretty large range, it's also consistent within 1 sigma, although it's not shown here. But the point is we can constrain the CO luminosity function, and especially this faint end, which is really hard to probe through galaxy surveys, at least not without a lot of expense. Right? If you want to know how this compares.
Can I just go back to that?
Yeah.
So you raised something that is not that well known, not known at all, which is, you call it the stochasticity of the CO, which, if you pull that in, it's not clear that you'd be able to get the kind of error bars, because it could be really pretty wild.
True, yeah. So. Yeah. So for what it's worth, the scatter in the model is parametrized. So that's allowed to vary within the MC.
Well, I guess okay. Maybe that handles the whole problem. I'm thinking about it in terms of actually looking at things on the sky, where some will have, way out on the tail of the CO, and another one which is a not very different galaxy. back the other way. And so the spread would just be potentially quite enormous to objects of more or less a given sort.
I guess, okay, sorry.
Or could be.
Yeah.
Tying that down by individual observations with some gold sample seems to me to be absolutely essential.
Sure, yeah. And so essentially what you want to do is you want to tie down basically this bright end with galaxy observations, with blind surveys if you can, right? And so
you're saying that you basically get to measure sigma t, the sigma L, whatever you call it, because the solenoid, because the scalar increase for solenoid. That's what you're claiming. You're not completely blown away by it because you're sensitive to a solenoid. Otherwise, I think it's saying, as I was saying, if you allow anything to float, then anything can go.
Right. I mean,
but your claim is that in your parameter scatter model, you actually measure the scatter, and therefore you actually get to say something about the remaining parameters.
Right. So the scatter is parameterized at the moment as a constant scatter, right? So as in constant over all halo masses.
Yes,
right.
But constraining it because you claim
right.
that you see the solenoid increasing if you make the scatter bigger, which is why
right.
if you didn't
if there is a more complicated form for that, or if there are other yeah.
Yeah, you're saying that the shape changes, and that's
the power spectrum.
The power spectrum would change, right?
Okay, right.
Yeah.
That's also a proof tool to try.
So there are certainly many degeneracies in the power spectrum. This is why it can't exist in isolation, right? It should also be informed by existing constraints. It's also why we need priors in our MCMC chain, or sorry, MCMC procedure. But to sort of touch on that point, if you're wondering how these stack up against observations, or at least current observations, what I'm showing here now in the gray band are constraints on the luminosity function from a blind CO survey, so a blind CO survey of the Hubble deep field, one of the Hubble deep fields. And so this is a Walter et al. 2014 observation that was done with PDBI. There are some large uncertainties here, and it's quite a small sample size. But I mean, this is it. There's not too much at the moment, right? This dashed dotted line here is the Obrezhkov et al. Is a modeled luminosity function from Obrezhkov et al. 29. They use what's called a semi-analytic model, and so the extent to which you trust it is up to you. But it's just sort of showing where this luminosity function stands in relation to these two things, right? And so you might actually ask very reasonably, are we fooling ourselves, right? Because we use the same model to generate the signal as we did to do the MCMC inference, right? So what we actually did here was we took the Obrezhkov et al. 2009 catalog, and so we went online. They have a database. We just downloaded the Galaxy catalog for the same volume, and then we generated CO luminosity, CO intensity maps from this, right? We ran our MCMC procedure again, and then these are the constraints that we get from both the Pathfinder and the full experiment. So the Pathfinder experiment is actually no longer sensitive to the signal because it's a much fainter one. And so you get this allowed region in here. But the full experiment is still sensitive to the signal. And you can see that within 2 sigma, for the most part, it's consistent with the luminosity function here.
So you used your model to fit a mock observation of something that was made with a different model. Yes.
Essentially, we're using what is in principle an independent model to generate the mock signal. And then we're using our model in the MCMC procedure. So this is not an exhaustive check. I don't want to give the impression that this is an exhaustive check, right? But it's to check that we're not fooling ourselves at the moment by using the same model going in as coming out. Okay. So I guess I also want to spend some time asking what would this look like compared to a blind survey? So if you wanted to reproduce this, but for counting individual galaxies, the best instrument to use at this point would probably be JVLA in this frequency band.
TBT, right? TBT, you would do the same survey in about 10 hours, and you would have the whole power spectrum with the ammonium array. You get 7 pixels, 20 Kelvin, 8 gigahertz bandwidth, and 100 meter dish, meaning you get to a K of about 10, and then you just measure the whole thing in no time. And you do intensity mapping.
What's the resolution of GBT?
At 30 gigabits?
Yeah.
20 seconds. No, but it doesn't matter. You get it all. You get the DC. The reason JVLA is not very sensitive is because you have to identify individual objects at high significance before you get anything. Because you're not sensitive to mean emission, whereas with GBT you don't have that problem. That's not going to with any meter.
20 arc seconds. 20 arc seconds is still not. So for example, let me just show you.
It's 10 times better than the.
But so at 20 arc seconds, you still have to worry about smearing over multiple objects.
Exactly, that's the goal. Right? The goal is.
No, what I'm saying is, how does this compare to a survey where you're looking for individual objects?
What I'm saying is, you can do the intensity mapping already today. You get it all, right? You don't get confusion for the sources,
right?
Bit, but you have redshift, meaning it's not that confused.
Okay.
And you also get all the intensity information, and you're done, and you can answer all the questions by just analyzing a few tens of hours of GBT time.
So is that realistic with GBT? I don't have GBT sensitivity information in front of me.
Yeah.
Is it realistic with the parameters provided?
Exactly. That's net comments.
I'd certainly be interested in looking into that, but I suspect that the integration times required are
10 hours, maybe.
To reproduce this?
Or produce the co-map specs.
Really?
Yeah.
Over 2.5 square degrees?
Over.
So the issue is, to do this analysis, you need some amount, you need a significant volume, actually, because you need to be able to resolve large-scale modes also. Right?
Understood. Anyways,
so
we can go over for DVD work.
Okay, yeah, I'd be interested in chatting about that if that's, yeah. Okay. If
well, I mean, I wouldn't like to say criticism, but the challenge is that people want a demonstration of doability for this.
And this is the signal, as he is saying, I don't actually know how much CO it is, so you don't know how big it you need to see anything.
So if that's viable, I'm certainly interested in chatting about that. At the moment, what I'm doing here is I'm comparing with a blind survey of individual objects, right? So if you wanted to look for individual CO emitters and count those up and get a luminosity function from that, what would that survey look like? And so you can go online, and there's an exposure calculator for JVLA. You can input all the parameters that you need. And so this is a mock-up of what that survey would look like. I've picked a random field within the Pathfinder field. So this is a 1.5 by 1.5 arc minute field. The beam size, or at least a full width half max, is that white circle there. So it's about 1.3 arc minutes. Right? And so you're looking for individual CO emitters. And the assumption here, which is very optimistic, is that A, the sensitivity is the same over the entire beam. And B, anytime you see emission above a certain threshold, above 5 sigma, you count that as a CO emitter. Right? So these are quite optimistic assumptions. But anyway, let's just run with them. This gray line here is a CO luminosity function within our volume. This black histogram is a luminosity function within this volume alone. So you can think of the black histogram as sampling the gray distribution. Right? And the difference between them gives you some idea of the sample variance errors within this field alone. Right? So with 1 hour on source of observation, you can get a couple detections, and you can get down to basically here, this red shaded region in the luminosity function. So it's not nothing. If you up it to about 10 hours on source, you get a few more detections. So now you're getting down to this part of the luminosity function. In principle, you're getting past the knee, but your sample variance error bars are so large, it's not entirely clear that you'd be able to say that robustly. Right? If you actually go a bit further and you request 100 hours on source, which is 4.2 days straight, if you go day and night, don't worry about the sun or any other observing conditions, you actually get quite a bit further down. And so you get to around 10 to the 9 on this distribution. But unfortunately, if you put on 100 hours on source, they actually ask you if you know what you're doing. And so they basically just check to make sure that you made a mistake or didn't make a mistake. So 100 hours is a very long time to request on VLA. If you just keep pushing forward and you go for 6,000 hours on source, which is 8 months straight, night and day, you're actually doing pretty well. So you're getting all the way down to the tail of this luminosity function. Right? But again, that's an unreasonable amount of time to ask for. And again, you have quite large sample variance error bars here. OK. So to bring this comparison home, what I showed before was this blind JVLA-like scan. The area of that compared to the area of our Pathfinder area is this small white square in the center here. Right? So you're probing a much smaller volume, hence these large variances. But with this experiment here, and with equivalent on-source time, you're probing down to a much fainter part of the luminosity's function. OK. So looking ahead, there's actually a question of whether we can push this to higher redshifts. And if you go to higher redshifts, you eventually reach into the epoch of reionization. This experiment was at 30 to 34 gigahertz, right? But if you go to half that, at about 15 gigahertz, then you push to redshifts of about 5 to 7. Okay. So there are two main questions in the epoch of reionization. The first is, how do galaxies drive reionization, if they do at all? The working hypothesis right now is that faint galaxy populations will drive the reionization process. And then conversely, how does reionization affect or alter galaxy formation in reionized regions? Okay. So the way to probe this would be to look at the galaxies and to look at the H1 distribution. Right? So this would be probed by galaxy surveys, presumably, and 21 centimeter maps. But unfortunately, if you look at the field for various galaxy surveys, the ultra-deep field, for example, is this tiny little square here. The ALMA primary beam at its largest, which is around an arc minute or so across, is this tiny little circle here. So in any given pointing, you have to worry a lot about sample variance from patch to patch. And if you look at the simulated 21 centimeter map on the right, you'll notice the morphology of the ionized bubbles is quite inhomogeneous on very large scales. And so this inhomogeneity is probably quite important. If you want to probe that, you need these large volumes and these large areas. And so the thought is, if we can take CO intensity maps and H1 maps simultaneously, could we learn something about the galaxies? And this is work for the future. So basically, CO would trace what's doing the reionizing, if it is star-forming galaxies. 21 centimeter would trace what's being reionized, which is a neutral hydrogen. OK, so in that case, let me just wrap up and end there. In summary, we've modeled the CO intensity mapping signal, and we find that it's detectable in the fiducial model from redshifts 2.4 to 2.8, at least. The galaxy halo connection, in other words, the LCO-halo relation, introduces these variations in the power spectrum, which we can measure with our experiment, which are within the sensitivity of our experiment. And so using an intensity mapping observations, we can potentially constrain the underlying galaxy populations. So in particular, we constrain the CO luminosity function and the infrared CO relation. Right? And so roughly speaking, these would trace the H2 mass function and also the star formation rate and molecular gas relation, potentially. Right? So these relations, the connection between CO and H2, as well as between star formation rate and infrared luminosity, needs to be looked at in greater detail at higher redshifts. But this is a step in that direction. Yeah, looking towards the future, I've mentioned this trade-off between area and depth. And so this suggests that we really do need diverse probes of the high redshift universe. And so the point that I wanted to make at the end was intensity mapping and galaxy surveys could be potentially complementary. So galaxy surveys would probe the bright end of the luminosity function and pin that down, while at the same time you could pin down or constrain the faint end with intensity mapping. And there are a number of issues to work out or look at going ahead. The first is, what do we get out of cross-correlation, either with other CO maps, with galaxy surveys in the same patch, or with H1, C2, or other potential lines? Right. Systematics and foregrounds are certainly something we need to understand more. And we need to know how to model them, mitigate them, and remove them in the final data analysis. But also there's a question of, can we use CO intensity mapping to trace large-scale structure and cosmology, or at least something like CO intensity mapping, after redshift 3, so out past redshift 3. And then if you go even further out past that, can we use it to trace reionization? So I'll end there. Thank you very much.
So like the motivation is to measure H mass Just wondering why would one want to do that? I mean, star formation rate you already know.
Yeah.
And it's because you want to understand star formation at that redshift? Is that the...
Yeah, that's part of the reason. We don't really understand how star formation, we don't have a full understanding of how star formation is fueled by molecular gas at those redshifts.
We don't even know what happens today, so what do we...
We know better than we know at redshifts 2 to 3. We can certainly trace CO in individual galaxies at low redshifts.
We can do that, and we just know it's complicated, right?
Right, but much of this cosmic star formation is actually happening at these redshifts. Right? So most star formation is happening at redshifts 2 to 3. I agree, it's not that we've answered every single question at low redshifts. It's just simply that we simply don't have measurements of the cosmic molecular gas. We don't have very good measurements of cosmic molecular gas at redshifts 2 to 3 at this epoch of peak star formation.
Now, they do have absorption measurements of all kinds of molecules and other things, and all kinds of redshifts everywhere. You didn't mention those, but is that actually not equally constrained?
Absorption measurements of which lines?
Absorption rate, I mean, in the DLAs, they get a whole zoo of just about anything, right?
Yeah.
I mean, it's you know, a few selected lines aside. Not
sure, yeah. Yeah.
Still, you know, these are massive, and you do know something.
And those are, yeah, those are certainly an important part of just getting a fuller picture of the gas content of the universe. Right. I think another thing that I kind of see here is we don't want just a single indicator of anything, right, in the universe. You want multiple probes of everything that you have, right? You don't want, for example, dust mass or infrared luminosity tracing molecular gas all the way back to redshift 6, right? You want different probes that you can correlate with each other.
Any other questions?